All right, let's continue now and take a look at how to handle problems that involve and. Okay. So the formulas that you see here for calculating the probability, where you're doing the probability of A and B, okay, really are just taking the formula that we had earlier for conditional probability that said the probability of B given A would equal the probability of A intersected with B over the probability of A happening. It took that formula and it just did some math and it multiplied both sides by the probability of A, okay, like that. And then that knocked out the probability of A that was in the denominator, and it left you with the probability of A and B being the probability of A times the probability of B given that A has happened, okay? So that's where it came from. Okay, I'm going to erase that. So it came from somewhere. Now when we did it, it really turned out to be more that we were using the number of elements, talking about the number of elements in A and B and the number of elements in A. So we had a kind of a different way of talking about it. But what I wanted to say about this is if A and B are any two events, you don't know whether they're independent or not, then this formula right here is the way you would calculate the probability of A and B. So when you're doing an and question, it's going to be a multiplication situation. All right? It'll make more sense when we do an example on the next in a second. All right? Now, if A and B are independent events, then that means that the probability of B given A happening is the same as the probability of just B, because A and B are independent, so it doesn't matter whether A happened first or not. So that formula looks a whole lot simpler, but it's important that you realize that formula only works if A and B are independent, because then we know that the probability of B given A equals the probability of B if A and B are independent. And people will forget to check that typically. They don't think about that sometimes. So my proposal to you would be not to assume this formula, not to try to see if that formula could be used. Just go ahead and always think about this, because this works in all cases. So always be thinking about, if you're looking for the probability of A and B, always do it probability of A times the probability of B, assuming that A has happened. Okay? All right, so let's take a look at how this might affect things. All right, and a little bit of a look at the notation. All right, so here we have marbles or balls, it says, in a jar. And I use balls in one place and marbles in the other. So let's just think of them as just little balls in a jar. All right, so we have 4 red, 3 blue, 2 yellow balls. So he's going to draw 2 balls from the jar, but it says without replacement. And our job is to find the probability he draws a red ball and then a blue ball. So first draw a red ball and then a blue ball, and the blue ball would be for his second draw. So you'll sometimes see subscripts like this that could be very helpful. So red ball first, and then a blue ball second, okay? All right, so if we're thinking about that, the probability formula that we just talked about up here, okay, would tell you, all right, think about doing the probability of getting a red ball first. All right, here's what you should just think. I need the probability of getting a red ball. Right now there are 4, 5, 6, 7, 8, 9 balls. 9 balls in the jar. The probability of getting a red one would be 4 out of 9 because there's 4 red ones. All right, now here's what all this means. You don't need to obsess about it. It's easier than it looks. It means, okay, now He did not put that red ball back in. So you had four red, right? 4 red, 3 blue, 2 yellow. Okay. You looked at the probability. He reached in. He's going to reach in and draw out a ball. The probability it's going to be red is 4 out of 9. Okay. So now what you think is, all right, then he'd be down to 3 red, right? Because it was done without replacement. So that red one he got is now out of the jar. All this is asking you now is what's the probability of getting a blue ball on your second draw, assuming that you got a red one on your first draw, right? So if you got a red one on your first draw, you're down to 3 red. So you don't have 9 marbles anymore, you have 8. And you wanted the probability of getting a blue marble, so we're using that as the numerator, and we are supposed to multiply those. And so we'll come up with 12 over 72. You could have simplified first if you wanted to, before you multiplied, or you could just now simplify, and we'd wind up with 1/6. So think about it that way. What's the chance of getting a red marble on your first draw? On my first draw, there are 9 marbles, and 4 of them are red. All right, then think, okay, now for my second draw, what's the probability of getting a blue marble? But I have to assume that I got a red marble on my first draw, and I have to make sure that I've paid attention to what happened to that first marble. Without replacement means that ball did not go back in the jar. So that means I have only 8 marbles, and 3 of those are blue, and that's where we would get our probability. All right, now this one is being done with replacement. All right, so if that happens, it's like you're starting over again. What happens on the first draw doesn't matter because the ball is going back into the jar. All right, so let's think about that. Oops. I realized I used marbles in one spot and balls in the other. All right. So here we have the same situation. The only difference is we're going to do it with replacement. So what's the probability it gets a red ball on the first draw? Well, there's 4 red out of the 9. All right. Then just ponder what happened to that red ball. It went back in. So for my second draw, I still have 9 marbles, and there's 3 blue ones, and so I still get that 12, but now it's over 81. And when I simplify that, that's going to turn out to be 4 over 27. All right, now, when you're doing it, I propose that you don't act like there's a different formula, but you always think, what's the probability of getting a blue on my second draw, given that I got a red on my first? And just ponder what happened to that first ball. So I'm still thinking this personally, but I'm thinking about how that red marble that I got first went back in. So before I did my second draw, I really had 9 marbles again. So I don't think of it as having 2 different formulas. I just think of the probability of the first happening and then the probability of the next thing happening. I always think of it that way. That way I'm more careful and I don't mess up the previous situation. All right, let's try this one. If 5 cards are drawn without replacement, I would recommend you look for that and underline it so that you pay attention to it when you're doing your work. We want, what's the probability that they're all going to be hearts? Okay? And we're drawing 5 cards, so I'm thinking about it like this. It's really an and question. It's what's the probability of getting hearts on your first draw and hearts on your second draw and hearts on your third. It's really an and. It's really probability of that, right? Probability heart first and second and third and fourth and fifth. So I'm going to think about that, and I'm going to wind up multiplying my results each time. And so I'm thinking about looking at my deck of cards. I'm looking at how there's 13 hearts out of 52 in those 52 cards. All right, now I got to think about what happened to that first card, because I drew it. You know, I'm reaching in and drawing a card, and I want the probability that it's going to be a heart. Well, there's a 13 out of 52 chance that it's going to be a heart. Now, what happened to that card? Okay, it stayed out without replacement. So that means before I make my second draw, you assume, or you realize that you only have 51 cards, and then you assume that first card was a heart, then you're down to just 12 out of 51. All right, so now that card is out of the deck. So now I only have 50 cards with only 11 hearts left, and then 49 cards with only 10 hearts left, and then 48 cards with only 9 hearts left. And so I have to work that out, and that's not an easy thing to type in correctly, so be careful. So on that one, you could type those fractions in with multiplication in there, but it's probably, let me see what happens when I do that. Probably your calculator is going to give it to you as a decimal, because it's kind of a weird one. Let me try it on mine. 11 50s times 10. Oops. 10. Messed it up. Shoot. Okay, hold on. I'm trying to type in 13/50 seconds as a fraction just to see what it does. Yeah, it turns out to just give it to me as a decimal no matter what. And the decimal I get is 0.000495198. All right, so they'll probably tell you to round. They might tell you to round to like 6 decimal places or something. So let's see, that would be 1, 2, 3. If we rounded to 6, 4, 5, 6. After the 6th spot is a 1. So if I rounded to 6 decimal places, I would keep all of that, and the 5 would stay a 5. Okay, so that's rounded to 6 decimal places. There's some problems where they'll ask you to round. I can't remember if they ask for it to be rounded to 6 or to 8 decimal places, but you'll get that later. All right, now if we were thinking about this, we actually could have used combinations to do it. I don't think it's as natural as just thinking about it the way I showed it, but I could have taken my 52 cards and chosen 5, and then when I'm looking at getting choosing 5 hearts, there's 13 hearts and I need to choose 5. I could have done that, and I would have gotten that same number as well. Okay.